Okay, so continuing from our self-inductance, now we're actually going to use, we're going to create, we're actually going to put an inductor, something called an inductor, into our circuit, which is a more practical way of talking about our inductance. So, let's recreate our circuit. Okay, here's our circuit. So we've got our EMF, and we have our resistor, and we have our current traveling around. Okay. And we know that the loop itself has this inductance to it, has a resistance to a change in the current given by this. We also know that L equals the number of loops times the magnetic field over the current. Times the magnetic flux over the current. Well, this was just talking about us going in loops around the whole circuit, but that's really impractical to keep hooking up this voltage each time to each loop. Okay, because the only thing we really need to change is if we change the area, then we can increase the flux, right? So instead of looping over and over and over again on the outside, we can create a loop, and I'm going to create a new color here. Instead of looping around and around again, we can create a whole bunch of loops right here. Okay, increase the number of loops, because loops are easy to make as long as we don't have to plug all this other stuff in there. And each time we put a loop, we're increasing the amount of area that has flux going through it, right? Create a smaller loop, but a whole bunch of them. And because we create a whole bunch of loops, we're multiplying the area each time we have a loop. Each time we have a loop, we're multiplying the area. Yeah? So, this is our inductor, and we call this L. And so now we actually have a fourth circuit element. Okay, we have our voltage, we have a capacitor, we have a resistor, and now we have the inductor, which is called L. Okay. It actually looks like this. When we put it in a circuit, it looks like this. It's just okay. It looks like a spring. Yeah, like you pull a spring apart. It's just saying that there's a bunch of loops there. Okay, it is an inductor. Okay, it has so many henries to it. All right. Okay, so what this looks like, this right here. Well, I'm not even sure I need to draw that. What this does, do you guys want to see what this is going to look like? It's really just a right? So it comes through here. Okay, it loops around. Okay, and it creates, what do we call this?
Something. The solenoid.
There it is. This is a solenoid. He beat you.
Very offended.
He beat you.
See you after school.
Maybe you guys should switch your college stuff.
Okay. So So comes in here, goes through the solenoid, comes out, and what you've done is you've created an inductor. And in the creation of the solenoid, we have a whole bunch of loops. Now we have a significant inductance that is more important than the self-inductance within the wire, within the circuit itself. Yeah? So now we can start doing some cool stuff with this. Okay, we had previously, if we do our voltage walk now, we have our initial voltage. Okay, come around, we have our voltage from our resistance. We have another voltage drop here. This is our back voltage. Okay, the voltage is pushing back. Okay, which is our voltage from our inductor. And then we come back to 0. But what is this?
Negative L plus
It is a voltage drop, so it does go into this equation as negative. Okay, so it's not in the circuit. It is a voltage drop. It does not increase the voltage. It decreases the voltage. Okay, so you could do a plus. You could do a plus EL if we wanted, but
So this absolute value gets plugged in.
yeah, yeah. Okay, this should look familiar to you. You guys seen this before? This was almost exactly the same as
The EMF.
the RC circuit.
Oh, RC.
Okay, is that exact? Okay, remember the RC circuit? Okay,
Capacitor.
remember tau?
Oh, kind of, sort of.
Oh, okay.
Like 10 years ago.
So, this is a differential equation. If you want to go through the derivation of how we come up with the next one, you're welcome to go to page 1007. Okay, and look it up. Here's our differential equation. Okay, you can look up at the solution. However, I'm going to take the easy way out. Okay, and I'm going to say it can be easily shown that okay, here's our current. E over R is the current, right? That is a tau again. Yes, it is a time constant. Okay, this time, it's not though. But you're on the right track. Okay, instead of being RC,
It's RL.
okay, it's not RL, but you guys are on the right track.
Negative RL.
Okay, tau, okay, is L over R.
So there's proof that
Okay, now go back and think about. Let's go back and look at this because this. Look at our units here. This is I. This is a current. This is a current. Okay. This has to have units of seconds to it. Okay, it does. Okay, you can go back and look at all the funky stuff, but this is in henries, right? So this is a volt per amp second, volt per amp per second, right? This has got some crazy thing to it. It's like volts per. It's volt. It's like volt second squared per coulomb, and if this is a volt per amp second, per amp per second, yeah, it winds up being. They flip around and you get this being a time. Okay, so interesting phenomenon. Okay. So here's our switch. If our switch goes here, okay, it comes in here, and this inductor begins to, I don't want to call it charge, but you create your,
Backward.
okay, what's that? Yeah, we start sending current through it, and we create this magnetic field. Okay, we create a magnetic field because our current is changing. However, tune in, guys. I know I put the switch in the wrong place. Darn it. Hold on, I don't want to confuse you with my switches here. It should go this way. So if I switch to here, okay, it creates we start building up the inductance. Okay, if we switch to here and this goes away, okay, this starts to this resists a change to a dissipation of current. Okay, so in other words, you flip the switch, it'll try to keep the same current. Okay, it'll eventually die down. It doesn't work all the way, but it'll try to keep the same current in there. And the current decays with I equals E over R e to the negative t tau. Okay, which if you look at your capacitance, the RC circuit, it's a very analogous equation. Okay, and that, you're going to need that for your RL circuits, for your homework. And that's that.